Hello everyone. Today is the 48th day of Leetcode 75 challenge. Let's begin with the 48th question. Question 994, rotting oranges. The level of the problem is medium. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Now let's understand the problem in the easiest way possible. Okay, so you are given a 2D grid representing a box of oranges of m cross n sign. Okay, this is what is given to us. Each cell in the grid can have the following values, either 0, which means the empty cell, 1 means a fresh orange, 2 means a rotten orange. Fine. So basically it would be like 2, 1, 0, 2, 2, 0, 0, 1, 2. This way. A rotten orange can spread rot to its four directional adjacent fresh oranges, which is up, down, left, right. This happens every minute. Okay. So your task is to find how many minutes it takes for all oranges to become rotten. So basically they are trying to say this is a rotten orange. It can rot the this four direction oranges in 1 minute. Okay, so in 1 minute it can rotate all these four oranges at a time. Fine. So we have to find how many minutes it takes that all the oranges present inside this grid becomes rotten. Okay, and if it is impossible to rot all the fresh oranges, we return -1 at the end. For example, if you are not able to rot all the oranges, then we return -1 in that case. Okay. The constraints of the problems are M is the grid length, N is the column length. This is a row, this is the column. And it could be from 1 to 10. Okay. And the grid IJ could be 0, 1, and 2, as we know from here already. So the question is pretty straightforward and simple. Now let's move to the next slide. Let's understand the input output of the problem. So you are given a grid. Okay. So here I can see we have 2, 1, and 1. Then I have 1, 1, and 0. Then I have 0, 1, and 1 in the grid. Fine. 2 means a rotten orange. Fine. Suppose and 1 means a fresh orange, 0 means there are no oranges, right? So if we start from this rotten orange, in 1 minute it can go in up, left, and right and down, all the four directions, right? So if I in first minute it will come here also and here also, right? So this will become rotten. Okay. Now if we take this rotten orange, it can rotten this orange and this orange, right? And the below one. Since below there is no more oranges, so this will get rotten. Fine. Now, if I take this, till now it took 2 minutes. Okay. If I take this orange, it can rot below orange also, right? And there is no orange here, so no need to consider anything. So in 3 minutes, it has rotten this much oranges. Okay. Now, if I take this particular orange, it can rotate this and this, right? But this is already rotten orange, right? So it will rotate this orange in another minute. Okay. Now, if I take this orange and I try to rotate this orange, it will take another 1 minute. So it takes now 5 minutes if we go this way. Fine. Let's take another way. Okay, we will start from here, rotten orange. In first minute, it will rotten this orange also and this orange also, right? Great. Now, if I take this rotten orange, and this rotten orange will rot this orange and this orange in the second minute. Okay. Now, if I take this orange, in the third minute, it will rotten this particular orange. Correct? Now, if I take this orange, it will rot this orange in the fourth minute. Right? Therefore, in 4 minutes, we will rotten all the oranges. Therefore, the output here is 4. Now, let's take the second example also. Here, it's given as 2, then 1, then 1, then it's 0, 1, 1, then it's 1, 0, and 1. Fine. Now, if we start from this orange, rotten one, it can rot in first minute this orange, right? Now, this rotten orange can rot this orange, and this orange is the second minute. Okay. Now, in the third minute, this orange can rot this particular orange. Okay. Okay, great. The fourth minute, this orange can rot this particular orange. But this orange will not be rotten or will not get rot because there are no more oranges which can reach here, right? Because this orange can go this direction up left and right, right, not diagonal wise. Therefore, it is excluded, and therefore the return answer is -1, as we are not able to rot all the oranges present in the grid. Fine. I hope you understood the input-output explanation. Before going to the further slides, let's understand what is breadth first search in graph. Okay, a BFS is a graph traversal algorithm that explores all the neighbors nodes at the current level before moving on to the nodes at the next level. So it is same as the level of the traversal of BFS in the tree. Okay, suppose this is a graph given to you. If this is the source, okay, and let's start. Okay, so this becomes level 1. This will be what? Level 2 for this source, fine, and this will be level 3, and this will be level 4. If you take this as this source node, fine. If you have taken this as the source node, then the graph would have changed, and this one and this one would have been the level 1. This one and this one would have been the level 2, and this might have been the level 3. So I hope you understood how we count or check for the labels in a graph. Okay. Now let's understand how we do that. So we just start from a source node, okay, and we mark it as visited. We enqueue into a queue because we are using a BFS. So we use a queue in this part. Suppose let this be the source node here, okay, and let it be 1, 2. I'm just writing random values, okay. Source is here, and since the queue is not empty, or while the queue is not empty, what you will do? You will pop this, fine. You will dequeue the front node. Now, after dequeue, you could do one thing. You could just put it in some list or something. Let me put it here, okay. Now we could visit all the unvisited neighbors of this particular source node, which are 1 and 2 in this case. So we put it 1 and 2, this is out, and we mark them as visited. Let this be this sign, let this sign cross sign be a visited one. Okay, fine. Now after that, you pop this one, pop, right? For the pop, you could see 3 is the level 3 node, we could say, right? So we will push 3 here, and as the source node is already visited, fine. So then you come to 2. So you pop 2, you put it in the list somewhere, and you check, okay, source is already done, so you cannot do that. So what you do, you take 4, right? So this is was the level 0, this was the level 1, this was the level 2. Similarly for 3 or 4, for 3 you will pop 3, then you will pop, when you will pop 3, you will put 5. This will become level 3. And when you will pop 4, you won't be able to push 5 because it is already visited. And at the end you will pop 5, and that's all. So this is how level wise we do the BFS calls, right? So this is the way we do the BFS call, okay? And BFS is a FIFO to keep the track of the nodes to visit next. So since we are using Q use the concept of FIFO. Now why is it efficient? Because time complexity is V plus E, where V is the vertices, E is the edges. Each node and edge is visited once, right? We have just seen it. And space complexity is OV, which is the number of visited array and queue, right? So you will have a queue which maximum size could be the length of a particular level or the number of nodes in a particular level. Fine. In this case, the length would be 2. Okay. And secondly, the array. Okay. The visit array would be of length 1, 2, 3, 4, 5, or whatever the length of the nodes are there, which is V basically. Fine. Okay. Now, why it is efficient for finding the shortest path in the unweighted graph, level or the traversal, cycle detection in undirected graph, connectivity checks in graph. So these are the way where you can directly implement BFS if you have the hint that okay, these are the concept of the question. Now, where BFS is used, okay, shortest path in unweighted graph. BFS guarantees the shortest path from source to the reachable nodes. Suppose Dijkstra algorithms could be one of the example. Useful in real world navigations, GPS, social networks, if someone asks you, fine. Connected component detections. In undirected graph, BFS can explore and label all nodes in a component. Repeated BFS helps detect disconnected parts of the graph cycles. Whenever you have to, Bellman-Ford algorithm, in Bellman-Ford algorithm, you could use this concept. Cycle detection. In undirected graph, revisit a visited node, not a parent. Cycle exists. In directed graph, BFS in degree tracking, Khan's algorithms helps detect the cycle. So these are the ways where you could use BFS. Yes, you could use DFS also, but in some cases using BFS is much more convenient than using DFS, right? So I have given some of the examples here, like using level order traversal in trees or graphs, like printing trees, etc. Bipartite graph is the common example of using BFS, and minimum moves in games like chess games and snake ladders. These are the basically practical examples. If someone asks you, serialization, deserialization of trees. Here, basically, we could use DFS also, okay, and BFS also. And since BFS and DFS both concepts can be used in graph as well as in tree, so I've mentioned both here. So I hope you understood the explanation of breadth first search in graph. Now let's move to the next slide. To understand what problem is asking, we should build up an intuition to the problem. Fine, let's do it by understanding the goal. So we are given a grid. We know that. Okay. Rotted oranges can spread rot to adjacent fresh oranges basically, which are in the direction of up, down, left, and right. Okay. Our task is simulate the spread rot and return how many minutes it takes for all fresh oranges to be rotten. So if you keep in mind that if this is your grid, you start from the rotten orange, because please keep in mind that we have to always start with the rotten orange. That is the thing which we have to understand. Okay. Now, if you have figured out that there are any fresh oranges left, we have to return -1 because we were not able to remove that, right? The idea is to perform some multi-source traversal. You can see we can start from anywhere in the grid, right? Therefore, it is a multi-source, right? Or we could start from all the rotten oranges. So that is the first thing which comes to our mind, that we have to start with the rotten orange so that we can rot the other fresh oranges. Otherwise, if you start with the fresh orange, there is no use of going or rot the other oranges because that is not possible, right? Therefore, there are multiple rotten oranges here, right? So that becomes a multi-source traversal. Now, what traversal could be used here more intuitively? Okay, let's take that now. Okay, so now we have to figure out what traversal which we could do, right? But if you keep in mind that we have to start with a rotten orange always, right? So if this is a rotten orange, we can go up, down, right, and left, right? And all these directions are taken in 1 minute itself, right? So basically, if four men are standing here, in first minute, all they will walk in these four directions. That is the thing which you have to do, right? And it will take 1 minute, right? So the traversal which helps in this particular thing is the breadth first search traversal or the level of the traversal, because for this particular shell, this is level one, okay? And for this particular shell, then for this same particular cell, if you go more ahead, this becomes the level 2, correct? So that is clear that since in first minute we have to check how many levels we go, or in first level how many rotten oranges are there. That is the thing which we have to figure out here, which we have already figured out. How to figure out, we have already figured out. So yeah, here we have to use BFS. So that boils down to our problem of using a BFS traversal in the graph. Okay. Now, first thing, we have to start with the rotten oranges. Okay. Secondly, we have to use BFS because, as I explained, in first minute, in first level, therefore, how many oranges are there, fresh or rotten, that we could rot, right? That is the thing. Now, third thing is there, how we will figure out that we have to start with the rotten oranges. Here we will use queue data structure. In queue, we will initially put all the rotten oranges, right? Because suppose if here is a rotten orange, right? And just take a hypothetical situation. If somewhere here you were only able to complete this part of the oranges. Just imagine you used rotten oranges, this one, and you were just able to complete this one, right? So what we will do? Here also, if you can see the example, since if we use this two, we cannot reach this one, okay? To reach one, we have to use this particular two or this particular rotten orange in the cell, right? Therefore, we will use Q and we will put all the rotten oranges there so that we could reach all the other unrotten oranges or the oranges which we have to rot. Fine. Okay, so therefore we will what we will do, we will put all the rotten oranges into a queue with their shell dimensions, basically rows and columns, so that we could start from there and we can look for the other oranges to rot. Fine. So that is what is written. I have written here. Okay. At each level, we will process current rotten oranges for each of their four neighbors. If it's a fresh orange, we rot it and add it to the level of processing. Each level of BFS is 1 minute fast. Yeah, that is understandable. If we reach the end of the BFS and some fresh oranges are still left, it means we're isolated and return -1. Okay. Now one more thing. You have completed the traversal using the BFS, right? And suppose if you were not able to reach, like here, if you were not able to reach the particular shell, right? How you will know that? For that, what you will do after complete traversal, since this is done, right? So you will make it two, will make it two. Okay. Suppose you were not able to reach this particular one here. After complete traversal of BSS, we will run a for loop with a complete grid, and we will check if there is any shell with the value 1. If it is, that means the all oranges were not rotten, all oranges didn't got rotten, and therefore the answer should be -1. So this is the thing, and I hope the visualization process was pretty easy to understand and simplify, right? It's just that we have to just figure out, we have to go with the PFS, and we have to store the rotten oranges with us. This is the two main things. Now how we can simulate this, right? We will treat every shell in the grid as a node in a graph, right? And first collect the position of initially rotten oranges, which will take some out m into n time complexity, and we will put it into a queue with time 0, right? Because if you start from there, the time should be 0, right? How we will be storing it? We will be storing it as row, column, and time. Okay. Now for every oranges in the queue, we check its 4 directions. Simple as that. And if it's a fresh orange, we change it to 2. If it is a 1, we will change it to 2. In queue, and we will increase the current time by 1. When one complete level is done, right? Then we'll increase the count by +1. Okay. We track the maximum time taken as we not reach as we route each new level of the fresh oranges, because it's a true thing that if you're routing this orange, you have to keep the count till now that how many maximum time you have taken. Okay. And if any oranges is left after that, after BSF we scan the grid basically using the for loop. If any of the shell is remained as 1, we will return -1 in that case. Fine. Now, what to figure out from the problem is that the problem reduces to a multi-source BFS form where all rotate oranges to spread not in the fewest minute. Basically, what we're doing here is that multi-source is reason being means Q we have stored all the source, you could say, source of the rotten oranges, right? Multiple sources. Okay. Now BFS deals here because it simulates spreading out level by level or minute by minute, right? In each minute in BFS we could go in 4 all directions, which helps in doing the thing which question is asking us to basically do. The maximum time encountered during BFS traversal gives the total time it took to reach all the oranges or make them all rotten. Fine. So I hope you understood the intuition is a pretty simple and straightforward. Now let's move to the next slide. Now, since you got the intuition of the problem, let's look into the approach how we're going to solve it. Fine. We will initialize variables and prepare for BFS traversal. We determine the number of rows and columns by taking n as the rows, m as the column. These are the common practices, right? We prepare a BFS traversal using directional array of 4 movements. This is the directional array, which I have explained in the previous problem also. Okay. It basically states that this is a number line, and this is a x-axis, this is y-axis, correct? And what we are doing here is that d row is basically our x, and d column is basically our y. Okay. So if I write it as -1 0 1 0 and 0 comma 1 0 -1, then it boils down to 1 comma 0. 1 comma 0 means column has not been changed, but the row has been changed. Okay, row, which means if you're standing here, came one -1 to the top in the row, and the column is same, right? So it becomes -1 comma 0 going up. Now 0 comma 1. Now 0 comma means this, right? Row 0, column 1. This means that we are going to the right direction. Okay, here, right. Similarly, 1 comma 0, the row has been increased, but the column is same, down. And similarly, 0 comma -1, the column has been reduced because we are moving to the left side, but the row is same. Okay, this is why we use d row and d column to make our four-way movement easier. We initialize a queue, okay, and enqueue the coordinates of initially rotten oranges with time 0 this way. Okay, the time variable is initialized to track the maximum minute passed as rot spreads. Okay, Now in step 2, what we will do? We will use a level-wise BFS. We begin with the BFS loop while Q is not empty. Simple code of BFS while Q. Okay. We will dequeue the items like row, column. We will dequeue them from the queue, right? We will take the maximum time also taken to reach in this row and column, right? The time which we store, suppose I am storing row, column, comma time. This means that time taken to reach this shell. Okay. So when we pop this value and the time, it means that to reach this shell, this much time has been taken till now. Okay. Now from this row and column or from this shell, we will go up, down, left and right, and we will record their time. Okay. Now in step 3, we'll spread the rotten or spread the rod to adjacent fresh oranges basically for each direction 0, 1, 2, 3. Okay, this is a for loop. Now how this happens is that we give a for loop from 0 to 3. Okay, and we take out the new row, the row which we popped, the D row value. So how this works is that D row will take this value. Okay, and the row value is already be taken here or which has been DQ. Okay. Now, suppose you got the shell value of suppose this 2 comma 3. If you have to go up, left, right, and down, what you will do? To go up, what you will do? You will see the row is reduced, right? So it will become 1 comma 3, correct? If you go down, it will become 3 comma 3. If you go to the right, it will become 2 comma 4. If you go to the left, it will become 2 comma 2, correct? And right in that scenario, for this thing we will do here. Here the actual row and column taken out from there, which is 2 comma 3 will be present. Okay, new column. Here, column will be present, which is 3, for example, and D column, I. So when the value of I is 0, what you will pop from the D row and D column? In D row, it is -1 and D column, it is 0, right? So here we will have -1 and here we will have 0. Our This equation will become the shell we will reach will become 1 comma 3, basically going up. Okay, this is how we will go in the four directions, and we will check if the grid is within the bounds. Basically, the row is within less than n, and if it is it is greater than or equals to 0. Similarly with the column. And secondly, we will also check that if this is okay, then we will check the grid of that particular new row and column is 1. 1 means that could be rot, right? If it is so, we will turn it to 2 and we will increase the time. That's all. I mean, step 4, after the BFS is complete, we'll check for the remaining oranges. Suppose BFS is done. Okay, we have the time. Great. Now, how do we know that if there is any oranges which didn't got rot, right? For that, there's one thing to do. Just traverse the grid again. It will take n cross n time and check if there is any shell with the value as 1. Okay, if it is, return -1, otherwise return the time. And at the end, we return the final answer. So these are the 5 steps to complete this particular question approach. So I hope you understood the approach explanation. Now let's move to the next slide. The code is the exact copy of the approach discussed. Let's understand it line by line. So these are the grid and this is the queue. Okay. Here we go through the complete grid and append all the rotten oranges into the queue with time 0. These are the row and column which I explained earlier. This is the time. Now here is the BFS which we will do. We will pop the row and column values along with the time. We take the maximum time taken till now, and then we will go all the four directions. We will check the condition if the shell is within the bound and if it is fresh orange. If it is, we used to convert it, append it, increase the time, again go for the loop. After that, we just run a for loop to check that if there is any one in the row. If not, return time. Okay. The complete time complexity is n cross n. Simple as that because it's a grid, n row, n column. Correct. Here also n cross n. Okay. And in the queue also, it will take approximately m cross n time complexity to traverse the complete grid. And space complexity is m cross n because q might take in the worst case scenario, m cross n. That means that all the oranges present in the grid are of value 2, or all the oranges present in the grid are rotten. Therefore, it will have total n cross n basically oranges in the queue, right? So I hope you understood the code explanation also. Let's move to the next slide. Now, since we have the understanding of the code, let's look at the dry run of the example. Okay, let me draw this graph here. 2, 1, 1. Okay, so I've drawn the grid. Now let's start. We have the m and n value. We have the queue ready here. This is the queue. We will traverse the complete grid. Okay. In this grid, we can see only 1, 2 is there, right? According to this thing. So what we'll do, we'll append the values. So it is 0, 1, 2, 0, 1, 2. So at 0, comma 0, we have the rotate arrange. So the time is 0 right now, and this is the 0 and the column. Okay. We pop the value. We pop the value in the row and column, which is 0 and 0, and also time, the tm, which is 0. Everything is 0 right now. Okay. Let me draw this queue properly. Let me draw it here on. Okay. Since we have popped this, we don't have any more in this in the queue. We check for the maximum time. Now, since both are 0, right? So it will be 0. The time will be 0. Okay. Now we'll go in the four directions here. This is important. Now, since we have, let me write it here. Okay. So this row and column stands for these values, right? We are clear to that thing. So we'll write 0 here and 0 here. And D row and D column. These are this list. And D row of I. Now I is now range is 0 first. Okay. So both zeros are here -1 and 0. Correct? So what happens? It becomes -1 and this remains 0. So -1 comma 0. Correct? Now n row, we check if the n row is greater than 0. No, it is not, right? So if it is not, if one of the conditions also gets false here, we don't do anything. We move ahead. Because it will be out of bound, right? -1 means. Okay. After that, this becomes 1. I will add 1 here. Not 1, sorry. B row of 1 is 0 for this and 1 for the column. So our new shell is in 0, comma 1. 0, comma 1 is this particular shell. Okay. It is in the bound and it is also equals to 1. So what we will do? We will make it 2. Okay. No, great. And we will append it into our queue also. And I will increase the time by +1. So it is 0, comma 1 and the time is 1. Fine. Great. We'll move ahead now. Now it becomes 2. So in the 2 we have 1 here and 0 here. Correct? So it becomes 1, comma 0. In 1, comma 0, we have 1 here, right? So this becomes 2 and we convert it to 2, right? And we put it into the queue also. It's 1, comma 0 with time is 1. Okay. Next, this becomes 3. So at 3, what we have? We have 0 and -1. So we got 0, comma -1. And since -1, it is out of bound, so we won't do anything. Okay, we'll just skip it. Great. So level 1 is done, right? Now we'll come back here. Now if we pop from the queue, we will pop what? We will pop 0, this one, right? So column was 1 and time was 1. And the row was 0 itself. Okay. So which means 0, comma 1, we are starting from here now. The maximum time was previously as 0, right? But now since Tm was 1 is 1, so the time becomes 1. Okay, let me write it here itself. Okay, great. Now again we will go into all the four directions. So it's 0, comma 1. So plus first is -1 and 0, right? So again it is out of bound or won't be considered because it becomes -1, comma 1. Second, it's 0, comma 1. So our new shell is in 0, comma 2. 0, comma 2, which means this. So this will get rotten. Great. Now after this we have 1, comma 0. So our shell is at 1, comma 1, which is this. This also turns to 2, right? We convert it from here itself. Okay, I forgot to do one thing. 0, comma 2 was also done, right? So we have to put it into the queue 0, comma 2 with time as 2. Okay, because time is 1 here, plus 1, it becomes 2. Great. Now we got 1, comma 1, this one. Okay, we will put it into the queue here. We will append into the queue 1, comma 1. And time was 1 previously, so plus 1 becomes 2. Great. So we have done two directions till now. 1, comma 0 is also done. Three directions we have done. Now we'll go for 0, comma minus 1. 0, comma minus 1 gives me 0, comma 0, which is already done, right? Because if you come here, it is not equals to the 2, so we will skip it again. Great. So level 2 is also done. Okay, now we'll restart again. We will pop this value 1, comma 0, comma 1, row 1, comma column 0, and time is 1 now, right? The maximum time was 1 here, and also we got 1 again. Fine. And it's 1, comma 0. This is 1, this is 0. So we're starting from here. Okay. So reduce this particular thing for you. Since this is already visited, it won't work. This is already visited, it won't work. It will go out of bound in the left direction. And this is there is no fresh orange here, so it won't come here, right? So here I just did this thing in a bit of shortcut here because there won't happen anything here, right? Therefore, we can skip this part. You can do your try run for this part by yourself, but I will skip it because it is getting longer now. Now I will pop this row 0, column 0, time 2. Fine. 0, comma 2 here. So what is 0, comma 2? 0, comma 2, we are standing here. Okay. Now, since we are standing here, just through visualization process, you could see that if you take out the maximum time, time becomes 2 here. Nice. Now, when we go to the four directions, without just doing a dry run, we can just check that this is already visited. We cannot go here because the condition falsifies here. If you go to the right, it will be out of bound. Up, it will be out of bound. So I just use shortcut here to skip this part, right? If you're willing to do the dry run, you could do it by yourself. So I'm skipping this part now. No. Now we'll pop 1, comma 2. 1, comma 2 with time as 2. Okay. Now here we will take max time and maximum time is 2, so no changes there. Now we'll go to the all four directions. 1, comma 2 means you're standing in the middle of the sorry, it's not 1, comma 2, it's 1, comma 1. Since it says 1, comma 1, right? Great. Now we're standing in the middle of the grid. Now we'll go at minus 1, comma 0 will do. So we'll get 1, comma we'll get 0, comma 1, right? And 0, comma 1 is this, which is already done. So we'll skip that. Now at 0, comma 1, we'll add 0 and 1 here. It becomes 1, comma 2. Now 1, comma 2 is this, but since it is 0, no need to go there, right? You can skip it. Then we can go, we will add 1, 0. So it will become 2, comma 1, right? What is 2, comma 1? This one, this value, right? Since it is a fresh grid and it is equals to 1, so we'll change this to 2. Okay. And we'll increase the time. Since time was 2, we'll make it 3 and put it into the grid. So it is 2, comma 1 with time 3. Nice. Now we'll take the last value, which is 0 and minus 1. So it becomes 1, comma 0, and 1, comma 0 is basically this direction, and this is already visited because it is equals to 2 now. So we'll skip that. So this traversal is complete in all four directions, right? Great. Now what we will do? We'll pop this. We'll take these values, right? We'll take the comparison. We had 2, now the time is 3, it will become 3. Okay, now we're starting from here. Now, if we take 1, comma 2 and 1 here, and if you take minus 1 and 0, it becomes 1, comma 0. Sorry, it becomes 1, comma 1. Now 1, comma 1 is already done, so we'll skip that. Okay. Okay. Now, if we take 0, comma 0, comma 1, so it becomes 2, comma 2. What is 2, comma 2? This shell, right? So this fulfills our condition here. So we will mark it as 2. We'll increase the count by 1. So since it was 3, so it will become 2, comma 2 with 4. Okay, this is all. Here I will skip the two transactions because at 1, comma 0, it becomes 3, comma 0, 3, comma 1, which is not possible. It is out of bound. and at 0 comma 1 it becomes 2 comma 0, and 2 comma 0 is this direction, and there is no fresh orange there. So this particular level for this particular shell is also completed. But since the queue is not empty till now, what we will do? We'll pop it. Now it becomes 2, 2, 4. We'll compare the time. It was 3, now it is 4, so it will become 4. And we could see, we will come back here again. We'll try to go in all four directions, but all four directions are visited. You can do the dry run for that. And after that, this is done. We'll come here. We'll traverse the complete grid, and we'll check if there is any one left. And since you can see there is no more any more one left, right? So at the end, we'll return the time. Time is what? It is 4. So I hope you understood the dry run. So if you have any doubts or confusion about the solution we arrived at, how we arrived at it, I would suggest going back and understanding the intuition, the approach, the code, and the BFS concept if you don't know. After that, do a dry run by yourself and post the examples, and I'm pretty sure you will understand both the solution and the thought process behind it. Now let's move to the next slide. Now, since we are familiar with the problem and the solution, let's move to the lead code and code the solution. So, okay, so we'll start with taking the row length, column length, initializing a Deque in Python for I in range n, for j in range n. If grade of I j equals to 2, q dot append I comma j comma 0. This is the time. Okay, and after that we'll take a time variable. We'll create the four-way direction list here: -1, 0, 1, 0. The column 0, 1, 0, -1. While q will pop the row and column, and the time q dot pop left. Okay, we'll take the maximum time, max of time comma tm. Go for the four direction. Prime range 4, new row equals to row plus b row of I, and column equals to column plus b column of I. If 0 is less, now we will check the out of bound condition here. If 0, or we could say n row is greater than 0 and less than n, and also same with the column. In the grid of the new shell dimensions, new row, new column, if equals to 1, then means we have got the fresh orange. Okay, now what we could do, could just take the grid of n row n column and mark it as 2. Okay, so it means that we have rotten this orange and append it into the queue again, and row and column with the time which we have got plus d1, current time plus d1, because we are going to the next level, right? This makes sense. After that, this traversal will check in row of the grid. We will go row wise. We won't be taking the column, not necessary. If 1 in the row, will return -1 directly. Okay, otherwise we will return the time. Let's try submitting the sample test cases. Okay, now finally submit the solution. So we have successfully submitted our solution. Now the code of the problem is available in the GitHub repository. You can find the link in the description. Thank you everyone.